An integral is called improper if one or both limits of integration are infinite, the function has an infinite discontinuity, such as a vertical asymptote at or in between the limits. Explain why each of the following is improper. Go ahead and try out A, B, C, D on your own and check your answer. If the result of an improper integral is a number, L, the integral is said to converge. If the result is infinite, the integral is said to diverge. Evaluate the following improper integrals, then tell whether it converges or diverges. So instead of having infinity as one of my limits of integration, I'm going to use the variable t. And then I want t to be the biggest possible number, or for t to be approaching infinity. Maybe t can't be infinity, but we could evaluate when it's approaching infinity. And what is the mathematical term for what something approaches? It's taking the limit. So the limit as t approaches infinity of the integral from 1 to t of 1 over x squared dx. In order to use the power rule, I'm going to actually rewrite this as x to the negative 2. Let's integrate. The integral of x to the negative 2 is x to the negative 1 over negative 1. We're evaluating that from 1 to t. We will evaluate the limit as t approaches infinity later. I can separate that limit, the limit as t approaches infinity of negative 1 over t, plus the limit as t approaches infinity of 1. Now evaluate the limits. Negative 1 over infinity is equivalent to 0. So this integral, this improper integral, has a value of 1. 1 is a number. It's not infinity. Therefore, this integral converges. Let's try number 2 in the same way. The limit of ln absolute value t as t approaches infinity is infinity. The natural log of 1 is 0. The result of this integral is infinity, so this improper integral diverges. Let's do number 3. Let's separate those limits. The limit of sine t as t approaches infinity. As t approaches infinity, you're jumping between 1 and negative 1. And so this is an oscillating function, and for that reason, the limit does not exist. So you have does not exist minus 0, which is just does not exist. Because does not exist is not a number, L, this improper integral diverges. Number 4, we're taking an improper integral of a product. OMG, I think we might get to use integration by parts here. So we've got several things to keep track of. First, we're going to do integration by parts. We also have a definite integral, integration by parts. The derivative of x is 1 dx. The integral of e to the negative x is negative e to the negative x. Let's use the formula for integration by parts with a definite integral here. All of that is within our limit. The integral of negative e to the negative x is e to the negative x. Continue to simplify. I'm going to evaluate the limit of each of these individual expressions. I'm going to take this negative out of the limit and then use the idea of relative growth rates to evaluate this. E to the t grows sufficiently faster than t, and if that happens with your denominator, then your result is 0. If that happens with the numerator, your result is infinity. Here our result is negative and then 0, which is just 0 obviously. The limit of a constant is that constant. The limit of 1 over e to the infinity has infinity in the denominator, so that is also equivalent to 0, leaving the limit or the value of our improper integral to be 2 over e, which is indeed a number. So this improper integral converges. Number 5 is an improper integral because a vertical asymptote is in between our lower and upper limits. You have a vertical asymptote at x equals 0. That is an odd vertical asymptote, so you do know the behavior on either side of it will be opposite. I'm going to sketch a quick graph to give me a visual. We are evaluating. So we're looking for the area of the orange sections. Because our vertical asymptote is between our limits of integration, I will need to split this integral into two separate integrals. One where we're taking the limit as we're approaching the vertical asymptote from the left, and one where we're taking the limit as we approach the vertical asymptote from the right. So if we're approaching 0 from the left, that would be from the negative direction. So we would start at the lowest limit, -1, and go up to t, which is 0 from the left. We'd have another limit showing the area of the second orange portion, 0 from the right. Our lower limit for this integral would be t, and our upper limit would be 2. Because the limits always need to be in order, least to greatest. Let's integrate and evaluate. Now I'm going to take the limit of each of these terms individually. I'm going to factor the -1/2 scalar out of this limit in order to visualize how I can evaluate this limit using relative growth rates. The limit of a constant is a constant, and I'm going to factor out the +1/2 out of this limit. I still can't use direct substitution with 0, so you can either plug in a really tiny number to the left and right of 0, or you can remember that 1 over t squared, or 1 over x squared, is one of your parent graphs. That has a vertical asymptote at x equals 0, and that's an even vertical asymptote. So the behavior on either side of the vertical asymptote is the same. That means the limit as we approach 0 from the left will be infinity. And as we approach 0 from the right, our limit is also infinity. Uh-oh, looks like we have infinities rather than an answer. Therefore, this improper integral diverges. You may be tempted to say -1/2 infinity plus 1/2 infinity, isn't that just 0? But remember that infinity is not an actual number. It's a direction, a concept. And so this infinity very well could be a different infinity than this one, which I know sounds crazy, but yeah, we cannot do arithmetic operations with infinity like that.